come back to this second half of today's lecture, where we are preparing to prove HNS3. This is the third formulation of Hilbert-Schulze ansatz. So, we have proved already lemma 1, and I need another lemma which is not so difficult. So, lemma 2. This is again a lemma from field theory actually. This is about the field extensions. So suppose, let y12 ym m is at least 2, m is at least 1 not 2, be indeterminates over a field capital K, then this K round bracket y12 ym, which is, this is the quotient field of Qt of the polynomial ring. So, elements of this field are precisely the rational functions, that is polynomial divided by polynomial. So, then this is not a K algebra of finite type. Remember, this polynomial algebra is an algebra of finite type over the field K, but if I take the quotient field, that is not anymore a K algebra of finite type. This is very important fact, and I will give you at least 2 proofs of this. The first proof will depend on the fact that this polynomial algebra over a field is a UFD, unique factorization domain, that one usually learns in the first basic course on algebra. So, that is called the theorem of Gauss. So, I will assume that. So, proof. So, how does one prove such a statement that it is not an algebra of finite type? That means we want to prove that it is not generated as a K algebra by finitely many elements. So, suppose on the contrary, that K round bracket y12 ym is a finite type algebra. That means what? That means it is generated by finitely many elements. So, finitely many f12 fr, where f12 fr are not polynomials, but they are rational functions. They are elements in K y12 ym round bracket, not the square bracket. But any case they are rational functions. So, I will again make the common denominator and assume that fi's are of the form some polynomials gi's divided by h, where the gi's are polynomials in y12 ym with coefficients in k, and this h is also an element there. H is also a polynomial in y12 ym, and h is not 0. So, if they have different denominator, then I will multiply numerator and denominator by more, and this fi will not change, but the denominator will be a common. This is a standard trick when one is applying this trick right from the school days. Alright. So, what does this equality means? This equality means that every rational function is a polynomial in this fi's over k. and once it is a polynomial in this, that means it's polynomial in these rational functions with coefficients in k. So that means I can clear this denominator again. So that will mean that every rational function will be, so this assumption, this, so then every element of this rational function field k y1 to ym is of the form some polynomial g divided by some power of h with the same h. So g belonging to k polynomial in y1 to ym, and s is some integer bigger equal to 1. 1 is needed because these fi's are of that form. Fine. It could be more, because if when I write the g, when this rational function as a polynomial in this, you might need to, that might come, a phi might come in that with power 2, because it's algebra generator, and therefore I have to clear h square. So therefore it will be like this. And I want to say now this is not possible, but this is not possible since, not possible since, at least I should give you an element, I should give you a rational function which is not of this form. Since this k y1 to ym has infinitely many prime elements, infinitely many prime polynomials. That we know, this statement is very easy. Why that? First, how do I apply this? So if this h is one polynomial, and therefore it will have only finitely many prime factors, and I am going to choose a prime factor which is a prime polynomial which is not a factor of h. So first let me finish why it is not possible. So for a prime factor for a prime polynomial pi in k y1 to ym with pi doesn't divide h, 1 over pi cannot be written in this form, g by h power s for any s. This is not possible. Why? If it is possible, if yes, then I cross multiply, and then we will get h power s equal to gh. So since, I will write in the bracket, since h power s will be equal to pi g, and pi divides RHS, which is LHS, which is h power s, and pi is a prime polynomial. Therefore if pi divides power of h, then pi will divide h, a contradiction. To the choice of pi. So if we know that there are infinitely many primes in this polynomial ring, then we are done. And how do you check that it is there, it has infinitely many primes? That is where we use the assumption m is at least 1. And why is that? For example, I will give you, so this I want to prove this statement that it has infinitely many prime polynomials. That doesn't require much space, so I will write here. So if m is bigger or equal to 2, just that means there are at least 2 variables, 2 indeterminates. Then look at the polynomials y1 plus y2 power n, where n is any natural number. All these polynomials are prime polynomials. That is easy to check. And if m equal to 1, there is a standard trick. If you have only finitely many primes, the Euclid's trick. If pi 1 to pi are the only primes, pi 1 to pi t are the only primes, then you look at pi 1 to pi t product and add 1 to that. And we know now this ring is a unique factorization domain. That means, and this polynomial, this is a polynomial, this is non-constant polynomial, therefore it should have a prime factor, and that prime factor have to be different from pi 1 to pi t. So that is the proof that this polynomial ring has infinitely many prime polynomials, and with that we proved that this 1 over pi cannot be in this form. So that means this statement is not true, that every element of rational functions is of the form this. This is not true, therefore our assumption is not true, therefore the lemma is true. So that proves the lemma. And I also said that one can also give a more elementary proof than this, which doesn't use the fact that the polynomial ring in finitely many variables is a unique factorization domain, but this simple proof I will write as an assignment. So okay, now we have prepared for the proving HNS3, and now I will come to the proof of HNS3. So proof of HNS3, and remember this is purely field theory statement. This is also called sometimes some books also call it a field theoretic form, field theoretic form of HNS. This is also known as Zariski lemma. HNS 1 is called some people call it algebraic formulation, because that gives a maximal ideal, and HNS 2 is the strongest one, which is also called a geometric formulation. All right. So what do you want to prove? We have given E over K field extension, and E is the field. E is actually field. If E is a finite type algebra over K, so E is generated by over K by x1 to xn, finitely many elements. Then I want to prove, E is algebraic over K. That means every element satisfies a non-zero polynomial with coefficients in K. So actually it is enough to prove that these xi's are algebraic over K. Alright, so that is what we are going to prove, and the proof I am going to give. So this proof is due to Emil Artin and John Tate. John Tate was a student of Emil Artin. All right. So we have this E, and we want to prove it is algebraic over K. So let us denote some notation. Let us call this put EI not EI, QI. QI, this is quotient field of QT of K. You take algebra, subalgebra of E generated by x1 to xi. This is an integral domain because it is a subring of E, subring of a field, and therefore it is an integral domain. Therefore quotient field makes sense, and I am taking I is from 0 to whole n. So what is the diagram? So when I take I equal to 0, it is a Q0 which is a quotient field of K, I 0. So there is nobody attached to K, therefore it is quotient field of K, but K is already field. So K is already Q0 contained in Q1 and so on. It is a chain, and the last one is Qn which is already E, because when I take I equal to n, this is already E, and E is given to be a field, therefore it is already E. So I have such a chain of fields. And what do I want to prove? I want to prove this E is algebraic over K. So let us put, let M equal to minimum of R such that this Qi plus 1 is finite over Q, over Qi. See, Qi plus 1 is somewhere here and Qi is here. So I take where this is finite over Q. This simply means that this Qi plus 1 is a finite dimensional Qi vector space. Look at all these i's and take, and I is varying from R to n minus 1. So what I am saying, look at this is if this is finite vector space, keep it, go to the next. If it is finite, keep it, go to the next one. So you choose R so that R is minimum with this property that all these later ones are finite vector spaces over the earlier one. So take such R. What does this mean? This means, no, what is to be proved now? See, if this is finite over Q, then it is already algebraic. So this is algebraic, this is algebraic, this is algebraic. So up to R they are definitely algebraic, and therefore we need to prove what? We need to prove that this R has to be, this minimum M has to be 0. So we need to prove that M equal to 0. Because if you would have proved M equal to 0, that means all these extensions are finite extensions, and finite extensions are algebraic, and algebraic property is a transitive property. So therefore if this is algebraic, then this is also algebraic. So I have to prove M is equal to 0. M equal to 0, that is, if I prove M equal to 0, then it follows that Qn over Q naught is finite and hence algebraic. But this is precisely En over K. Finite field extensions are algebraic. So as I said, actually this proof also shows that we are actually proving it is finite. Alright. So we want to prove M is 0. So if we assume, so So, suppose on the contrary that M is positive. On the contrary that M is positive, then we are looking for a contradiction. All right. We are looking for a contradiction. So let us see. All right. So let me draw this Q0 is here, Qm is somewhere here, and Qm plus 1 is here, and this is Qn here, which is E here, and this is Qn minus 1, and so on. And this is finite, this is also finite, and now this is not finite, Qm minus 1, this is not finite. That is how we have chosen our M. So this is by choice of M. And obviously we are assuming M is positive. All right. So what is Qm? So note Qm was what? Qm was the quotient field of, you take that field earlier one, Qm minus 1, and the attach Xm. Actually Qm was by definition it was the quotient field of this integral domain x1 to xm. But this is same as this is not same as this, but because this is a quotient field and this Qm minus 1 is also contained there, because this is a quotient field of Qm minus 1 is a quotient field of K x1 to xm minus 1. So this is a field, and therefore this is a smallest field which contain kx1 to xm, and therefore both these are equal. All right. So then we know by what did we prove in lemma 1? So here it is. So I will write here by lemma 1. Qm is a K algebra of finite type. Remember what is lemma 1? Lemma 1, if you have an in between thing, that is this is my R, this is your B, and this is our K. So this is A, this is R, and this is B, and this E is finite over Qm that we know, and this Qm over this is this is a ring in between, and so therefore checked by lemma 1, this is actually K algebra of finite type. So I will show you what we proved in lemma 1. So here this situation, this B was our E is an B is a algebra of finite type, that is the assumption we have given in HNS 3. This R, B is finite R module, that is also given by our choice of M. And then what is the conclusion? This A is Noetherian, but A is our field K, therefore Noetherian, and the conclusion is this R is an A algebra of finite type. That is precisely what I have written. See here. So here I will say apply to A equal to K R equal to QM and B equal to E. So therefore it is an algebra of finite type. Alright, therefore we will consider therefore I want to clean up little bit notation. Therefore we reduce to the following case. So E is a quotient field of some subalgebra. See, this is generated by one element only. So I want to enlarge, I want to forget K and work with Qm minus 1. So let us look at the situation. This is my K, which is Qm minus 1, and then this one is, next one is Qm, which is Qm minus 1 xm, and this is contained in E. Ultimately we want to get a contradiction. So I will forget this E and call this as E. So in the new notation, this is my E. So I will forget this E and call this as E, and forget this Q and call this Qm minus 1 as Q. And now I want to get a contradiction to the fact that this is a K algebra of finite type. Alright, so this is, if it is a K algebra of finite type, then it will be K algebra of finite over Qm minus 1 also. So we are in this situation. E, this is the quotient field of the subalgebra Kx, where K is a field and X is an element in E, and this Kx is therefore K subalgebra of E. In this situation, we are in this situation, and this is not finite, and E is not finite over K. That is how we have chosen our M, that this is not finite, this is not finite. So this is my K, this is my Kx, and so we are in this situation. And what do we want to prove? I am looking for a contradiction, because we assume that this M is positive. So looking for a contradiction. Alright, so there are two cases. So case 1, X is algebraic over K or not. X is not algebraic over K. There are only two possibilities. I will say that the first possibility doesn't occur. Why? Because if it is algebraic, then this is a finite dimensional vector space, finite dimensional K vector space. But that is not the case. We are assuming it is not finite dimensional. So we are assuming, remember, we are assuming it is not finite dimensional by our choice of M. So this is not possible. This is not possible. Not possible. by choice of M. Alright. So, it is not algebraic. That means what? That means it is transcendental. So, that is this Kx is a polynomial algebra. It does not satisfy any polynomial over K. That means this is a transcendental element. So, this is isomorphic as K algebra isomorphism. That means the map which sends this capital X to small x, this is clearly surjective, and also it has to be injective, because if it is not injective, the kernel will contain a non-zero polynomial in that, and that will mean that X is algebraic. But because of our assumption X is not algebraic, that has to be an isomorphism. So, this is isomorphism as K algebras. And now, what is E then? E is the quotient field. So, but then E is nothing but the quotient field of the polynomial algebra in one variable, which is field of rational functions. So, this is the field of rational functions. Functions in one indeterminate x over k. And what do the by lemma 2 says? Lemma 2 says such a field of rational function, the variable is at least one that cannot be finite type over k. So, and by lemma 2, E is not K algebra of finite type. But that which is a contradiction. You see, because you look here, what we are assuming. This is so this is finite, this is by lemma 1, this is finite type. This was finite type over E, but that is the quotient field of this, which is C, and so therefore it is not possible. Therefore, so this proves that M must be 0, and hence E is algebraic over K. In fact, E is finite dimensional K vector space. So, this completes the proof of HNS3. So, with this we have proved all HNS1, HNS2 and HNS3 and their equivalence. So, this is a big step. This is in fact the beginning of modern algebraic geometry, and in the next lecture The next 2 lectures I will draw a lot of consequences from Hilbert-Null standards, where I will be allowed to use any formulation that one likes, because we all know that they are equivalent. So, I will draw many nice applications of these Hilbert-Null standards. Some are geometric, some are algebraic, and that will give us an interplay between algebra and geometry. Some results which look harder to prove in geometry, we will prove them precisely by using algebra, and some results which are algebraic will be proved by the geometric statement. And then further we will strengthen this study and study more basic properties of the Zariski topology and their algebraic meaning by using the Null standards. So, with this I will stop, and we will continue in the next lecture the consequences of Null standards. Thank you.